Good morning, good afternoon, good evening, good night, depending on when you're watching this video. In this video, we're going to work through the second exercise on computing confidence intervals that's given on slide 17 of lecture set number 7. Okay, so at this point, we've seen one example and one exercise that show the construction of a confidence interval when the population standard deviation is known. We're going to continue to work through those types of construction now. You can see in parts A and parts B that we have sigma equals 2. So that's sort of an indication that we're going to be using a confidence interval based off of a Z-score. All right, so let's get into it. Here we have question 2A. From a SRS of 725 adults, the belief is that 3.14 children is the ideal number for any family on average. All right, so right off the bat, what we are actually being told here is that n is equal to 725 and that x bar is equal to 3.14. Right, so we are being given the sample size and the average from this sample, right? So the 725 adults in the sample returned an average estimate for the ideal number of children of 3.14. So that's the sample mean. Okay, we want a 90% confidence interval for mu if sigma equals 2. So the first thing that we do is we write down our assumptions. So again, there are 3 assumptions or 2 assumptions and a check, depending on how you want to think about it. The first is that a simple random sample was collected. We can see from the problem description that this is in fact the case. The second assumption is that we can consider x bar, the sample mean, to be normally distributed, right? So we can write this as x bar is normal. All right, now we are not told the distribution of the ideal number of family members, which is the variable in this case. But what we do know is that the sample size is 725. So because the sample size is 725, we can assume that x bar is approximately normal because of the central limit theorem. So the central limit theorem says if the sample size is greater than or equal to 30, then the distribution or the sampling distribution of x bar is approximately normal. So here we can say check, and then we can make a note. This is by the central limit theorem. Okay. Okay, number 3 is sigma known. And you can see in this question, we are told sigma is equal to 2. So in that case, it's checked out. All right, so now we can begin to build our 90% CI. Okay, so the first thing on step 1, we have the 90% confidence level. So that means alpha is 1 minus 0.9, which is 0.1. Okay, so that means that we have z alpha over 2 is z 0.01 over 2, which is z 0.05, which is 1.645. Okay. And again, just in case you're wondering where that value came from, but at this point, we've seen many illustrations of computing this value. If this is a standard normal curve here, we have z 0.05. So this is a size 0.05, which means that this is a size 0.95. And then if we look up 0.95 in the standard normal table, you can see that I've done this in the previous illustration as well. 0.95 in the table corresponds to the score 1.6 and the average of 0.04 and 0.05. And this is a unique Z-score. This is one of 2 or 3 Z-scores that we can write to 3 digits. In part B of this problem, I'm going to show you the other one, or one of the other ones. So this is a value of 1.645. Right? So that's where this number comes from. Now we can compute the confidence interval. So we have X bar plus or minus Z alpha over 2 multiplied by sigma divided by the square root of n. So this is 3.14 plus or minus 1.645 multiplied by 2 divided by the square root of 725. This gives us 3.14 plus or minus 0.122. So then if we add and subtract 0.122 from 3.14, so we would have 3.14 minus 0.122, 3.14 plus 0.122. We end up with 3.018 to 3.262. All right. And then we can say something like, we are 90% confident that this population of adults believes that between 3.018 and 3.262 children is the ideal number on average. All right. Okay, in part B, it asks us to compute a 99% confidence interval. So this process is going to be exactly the same as the one that we had just undertaken, including the assumption check. All of that's going to be identical. The only difference is that we are changing the confidence level, which means that our Z-score is going to change. So in part B, we would start with the assumptions. And they are exactly the same as the assumptions in part A. The sample hasn't changed. The population hasn't changed. Nothing's different except the confidence level. So that doesn't affect the assumptions. So we still have a simple random sample. X bar is still normal by the central limit theorem. And sigma is still known. Okay. All right. So for the 99% CI, on step 1, we now have the 99% confidence level. This means that alpha is going to be 1 minus 0.99, which is 0.01. So we are going to have a Z-score. Z alpha over 2 is Z 0.01 over 2, which is Z 0.005. All right. So the way we find this value is still exactly the same. We have a sketch of a standard normal curve here, centered at 0, and now we have Z 0.005 here. So the only difference between this Z-score and the last Z-score is that this Z-score is going to be bigger because there's less area in the upper tail. So this is now a size 0.005, which means that this is now a size of 0.995. So if we go to our standard normal table, okay, we're looking for 0.995. Right. So you can see 0.995 is directly in between these two quantities here. So this is an example again of a 3-digit z-score where we are able to round. Okay. So we are taking the average of 2.57 and 2.58. Okay, so the average of 2.57 and 2.58 is 2.575. Right, so this is the same process that we had in the 90% case. This again is an example of a 3-digit z-score that derives from averaging. So this is one of the other examples of a 3-digit z-score that we can utilize. And given that value, we can now plug in. So we have x bar plus or minus z alpha over 2 multiplied by sigma divided by the square root of n. So that's 3.14 plus or minus 2.575 multiplied by 2 divided by the square root of 725. That gives us 3.14 plus or minus 0.191. And the result, so if we add and subtract 0.191, we have 2.949 to 3.331. All right. Okay, so then we're actually going to have the exact same conclusion that we had in the previous step. So just going to be a little cheeky here. I'm going to copy and paste this. All right, and then the only thing that's going to change is the percentage and the interpretation. So we now would say we are 99% confident that this population of adults believes that between 2.949 and 3.331 children is the ideal number on average. Okay. In part C, it asks, for n equals 725, which is the sample size we're working with, which interval will be more accurate? All right, so basically, what we have learned previously is for fixed sample size, increasing confidence level decreases accuracy. Okay, so for the same sample size, if we increase the confidence level, the accuracy of the interval goes down. So in this case, therefore, the 90% CI is more accurate than the 99% CI. Okay, in part D, it says verify this result. Okay, how can we verify accuracy? Okay, so we can say the more accurate confidence interval will have a shorter length. Okay? The length of an interval is equal to upper bound minus lower bound. Okay, so the length of the 90% CI is equal to 3.262 minus 3.018. All right, and that should be 2 0.44. And the length of 99% CI is equal to 3.331 minus 2.949, okay, which is 3.82. Therefore, the 90% CI is more accurate as it has shorter length. Okay. So in this illustration, we saw two examples of computing confidence intervals, which were exactly the same because nothing changed except the confidence level. We then compared, or we then were asked a question about accuracy. Accuracy for a confidence interval refers to how long the interval is. Okay. So in this case, or for the same sample size, we know that increasing confidence level decreases accuracy, which makes sense because if you look at the structure of the confidence interval, we have X bar plus or minus Z alpha over 2. The Z alpha over 2 value has gone up as the confidence level has gone up. So you're multiplying by a bigger number. That makes the interval wider or gives it a greater length. We're asked to verify this result. So we compare the lengths of the 90% CI to the 99% CI. And we can see that the 99% CI is longer, therefore it is less accurate. Okay. The other way we can do this, which is more direct, is just to compare the margins of error directly. The interval with a larger margin of error is going to be less accurate than the interval with a shorter margin of error. All right. As always, if you have any other questions, please let me know.